Okay, so the topic for today is primal dual algorithms for min cost perfect matching. And specifically, the agenda for today is to cover something called the Hungarian algorithm. Okay, so let's discuss the setup of the problem. So G, and so the vertices, or VLVR, is a bipartite graph. Bipartite graph where edges have weights. So instead of costs, I'm actually just going to think of it as a weight, where edges have weights. And the problem is to compute a perfect matching of minimum weight. And I'll just sketch out that, you might think that the more general problem is to compute a maximum matching of minimum weight. So we can easily convert a max matching of minimum weight to perfect matching of minimum weight. And I'll just draw a picture, and hopefully that picture will convince you. So suppose you have VL and you have VR here. So what you do is you can add some dummy vertices, and you just, for every edge, put every, I'll say, extra edge with weight something like W, where W is more than the sum of all weights. So what you can do is you can basically put all the other edges of essentially like infinite cost or infinite weight. And so when you do this, the total, you can argue that the minimum weight perfect matching in this graph will actually give you the minimum weight maximum matching. So it's a fairly straightforward reduction. And so we will assume that G has a perfect matching. And it just makes our discussion a lot easier when we assume that G has a perfect matching. So how do we do this? So you can reduce this problem to min cost flow, and you can solve a min cost flow. Although it's nice to see. We'll see a very nice direct algorithm, and this is going to introduce some topics that I will cover in more detail over the next few lectures. So note that we want an integer solution, which is a matching. So we write an integer program. So this is not a linear program, but this is an integer program, or technically an integer linear program. So we'll say that we want to minimize the sum over all edges of the weight of the edges, or the cost of the edges, whichever way. So I will stick with CE, but which you can think of as a cost or a weight, times XE, with the constraint that because I want a perfect matching, I want for all vertices in V, for all the vertices, I want the summation of X, I'll say V W, where W is in the neighborhood of V, this has to be 1. And you can write, the constraint VW or WV depending on whether it's on the left or the right. So now I'm just going to sort of write it this way. And furthermore, for all edges, I want XE to be in 0, 1. So this looks like an LP. But this is the integer constraint. What I've written here is called an integer linear program or an integer program. Any questions at this point? Does this make sense? Okay. So this is an integer linear program. Unfortunately, solving IPs, this is called an IP as opposed to an I, or sometimes called an ILP, or sometimes you'll say IP. Solving IPs is NP hard. Unlike linear programs, which can be solved in polynomial time, integer programs cannot be solved in polynomial time. So what we do is something called a relaxation, or sometimes called a continuous relaxation. What we do is we replace this integer constraint by a linear constraint. So this is the relaxation of the integer constraint, into a linear constraint. Another way to think about this is to, instead of having integer variables, we will replace them by continuous variables. This is a very, very important concept in optimization, especially combinatorial optimization, where you're looking for your solution space is a bunch of discrete objects which are matchings. And so you can write an integer program whose solution will be like the optimal discrete object. What you get but we don't know how to solve these efficiently. So we replace the integer constraint by a linear constraint, or you can think of it as we replace the integer variables by continuous variables, and this program we now know how to solve. Does that make sense? Any questions? Of course, you might ask, okay, but now that you've written this integer program, like what's the utility of the linear program? Well, you wanted to solve the original program. In this case, it turns out, remarkably, that essentially this is equivalent. And this is a theorem of Burkhoff from 1947, which says that if the LP above has an optimum, then there exists an integer optimum. And technically I mean an integer valued optimal point. And this is also referred to, and I will discuss this more in further lectures, but I'm just going to write this out over here, and then we can discuss this. Later. Is that the polytope given by these constraints, the summation x vw is equal to 1 and xe is greater than 0. This polytope is integral. This is an equivalent, an alternate statement. Basically, this means that the vertices of this polytope are integral. And we will discuss this later when we talk about the integrality of polyhedra. But what is important is that you understand what Birkhoff's theorem is saying. It says that even though you replace the integer constraint by a linear constraint or by a continuous variable, somewhat magically, the solutions, you can always find a solution with integer points. There also exist solutions that are not integers, but what it says is if there exists an optimum solution, there will exist one with integer values, and hence, essentially, if you solve this LP, you solve the discrete problem. Okay, so any questions about this? This is a very important point, so I want to make sure that I answer any questions if there's any confusion about this. Okay. I also want to emphasize that this is only true if G is bipartite. Or I should maybe not use the word only, overload it. It's true if G is bipartite. If G is not bipartite, the story is a lot more complicated. And in general, this is not true. Birkhoff's theorem is false. But when the graph is bipartite, this is true. So what this says, let's zoom out a little bit. What this says is we can use LPs to find the minimum weight perfect matching in bipartite graphs. What is nice is you can even do maximum weight perfect matching, right? Because you can replace the min by a max and you still have a linear program. Indeed, you can give any constraint that you want over here. You can give any linear constraint and this problem is still solvable. Like any linear objective, any linear objective. So it can be a maximization, it can be a minimization. So this is a very powerful and it's a statement. It's actually fairly easy to prove, Birkhoff's theorem, and I will prove this shortly. And I'll just give you an explanation. The Burkhoff, this is called the Burkhoff polytope, is essentially the polytope that I've given here. The polytope where G is equal to K and N. Like G is the complete bipartite graph. So when G is the complete bipartite graph, then this polytope is called the Birkhoff polytope. Indeed, the vertices of the polytope are the incidence vectors of perfect matchings. Okay, but let me, I've thrown this out there. I will, in 2 lectures, when I talk about the integrality of polyhedra, I will get into more of this. For now, the only thing that we need to look at is just the statement of Birkhoff's theorem, which is that if G is bipartite, If the LP above has an optimum, then there exists an integer valued optimal point. Okay. So now that we have a primal, just rewrite the primal here so that you can see it. It's the min of summation E CE XE, and then for all V, you have the summation of XW is equal to 1, where W is in the neighborhood of V, and for all E, XE is greater than 0. So this is the primal problem. And now let me write the dual as expected. So I'm just going to write out like sort of this matrix picture of the primal dual problem. So here is C. Here's my constraint matrix. Right? So this is constraint matrix times some x. And this is equal to the all ones vector. And I have x is greater than 0. Right? I have a non-negativity constraint. Okay, let's look at any column of this matrix. What does the column look like? So remember, a column corresponds to some edge. How many non-zeros are there in this column? So I want to write the dual. So how many columns are there in this? I'm sorry, how many non-zeros are there in this column? What does this column look like? Remember, there's a row for every vertex. Yes? What does each column of this matrix look like? Any thoughts, any suggestions? What is the column of this matrix? What is the row of the matrix? Yes, any guesses?
Each row should only have one, and the others are zeros.
Sorry, say it again.
Each row will have only one coordinate who is 1, and all the others are 0.
Why do you say that? So each row corresponds to this constraint here.
Mm-hmm.
So each row has actually many variables participating in it.
Right.
So actually each row is going to have a 1 for everything in the neighborhood. Does that make sense? So this is actually, the row is going to, so the row corresponding to V is the incidence vector of the neighborhood of V. Right? Because you're going to have one variable for each. Well, the edge incidence vector. Does that make sense? So for every edge that V is incident to, so if you look at some vertex V, and it participates in a bunch of edges. So there is a coefficient, a non-zero coefficient for each of these edges, and that's exactly what the column is, the row is going to look like. Does that make sense? Does that clarify that?
Yes.
What about the column now? Consider any edge. How many constraints is it going to appear in? How many constraints does any edge appear in?
2.
2, exactly. 1 for each endpoint. Right? So if you have this UV, it's going to appear once over here and once over there. And it's all with positive, just +1 coefficients. So note that the dual has a variable for every constraint. So the dual is going to have this variable YV. Right, so YV. And every constraint in the dual, so there's going to be a constraint for every edge, where you just take YU plus YV. Now note that this is a minimization problem, so the dual is going to lower bound things. And so what you are basically going to get is, something of that form. And of course the objective function is just going to be the sum of the dual variables. So the dual is going to be a max over all vertices of YV, right? Because you're just going to maximize over the sum of all the dual variables. The constraints, and note that it's essentially, because these are all equality constraints, the YVs are unconstrained. And then what you have is for every edge, we will have one constraint that basically corresponds to the column of the matrix. Sorry, just 1 second. Okay, so for every edge UV, we're going to get the constraint YU plus YV is at most CE, right? Because this would be CE over there. So YU plus YV is at most CE, that's the dual. Any questions about this? This is a good time to ask me why some things are one way or the other if you're trying to understand duality better. Any questions about what the dual? All right. And so now let's construct our primal dual algorithm. So we maintain a partial matching that's given by x. So x is just going to have values in 0, 1. I mean, every coordinate is going to be in 0. It's just going to be a partial matching. It's the incidence vector of a partial matching. We maintain a feasible dual solution y. So we'll maintain some y which always satisfies these properties. Remember, the primal solution, the primal is not satisfying all of these properties. Indeed, it is actually going to fail some of these constraints. So we maintain a partial matching. And we maintain complementary slackness. So let's write out what the complementary slackness conditions are. When you look at the primal and dual, the only inequalities are here. This is the only inequality constraint. So what we know is that the variable corresponding to this constraint. Now what is the variable corresponding to this constraint? This is actually the primal variable xe. And so we know that either xe is 0 or the constraint is tight. So another way of saying this is the complementary slackness conditions say that xe is non-zero implies yu plus yv is equal to ce. This is the complementary slackness condition. So we are going to basically maintain the partial matching maintain a feasible dual, and always keep complementary slackness. And when we finally get a perfect matching, we automatically have the optimal solution. And this is because a perfect matching is primal feasible. And we know by the theorems that we've seen so far that when you have a primal feasible point, a dual feasible point that satisfy complementary slackness, then both of them are optima. Okay, this is the way it's going to work. Any questions? Any questions? Right? Now let's investigate this notion of complementary slackness a little bit more. So just as we did in min-cost flow, we'll say an equality edge is an edge UV where YU plus YV is equal to CE. That's an equality edge. We will refer to the set of equality edges. We will refer to this as E equals. This is the set of equality edges. Now the complementary slackness conditions is simply saying that x uv equals 1 implies that uv is in this equality set. Equivalently, we maintain. So instead of talking about x, I can just talk about we maintain a matching, which may be partial. We maintain a matching M such that M is always a subset of the equality edges. So this is the game now. The game now becomes maintain a matching which is a subset of the equality edges and keep trying to augment and increase your solution, increase the size of the matching while maintaining this condition, which is the complementary slackness condition. So given matching M in the equality set, we try to extend M, extend or augment M. Always, I'll say this, we try to extend M within the equality set. If we cannot, we update the dual. Right? And this is the whole primal dual schema summarized in 2 sentences. We start with a matching, we try to extend the matching within this equality set, within this set of equality edges. If we cannot extend the matching, then we update the dual, and we keep trying to do this. And what we want to show is that if we, run this in the appropriate way, then this process will terminate in polynomial time. Any questions about this? Any questions about this? So I'll pause here. All right, so having discussed the basic primal dual schema, we use M alternating trees, and this was used first in the Blossom algorithm. So let me just pull up my previous notes on alternating trees. Recall that an alternating tree starts from an M exposed vertex. So this is some vertex S that is not matched by M. And then the alternating tree takes a non-matched and unmatched, so an edge that's not in the matching follows the matching. Then an edge not in the matching follows the matching, so on and so forth. And remember, we colored the vertices alternately blue and red. So the root was blue, and all the other vertices are red. Blue nodes are at even distance, red nodes are at odd distance. Blue nodes have many children, red nodes have only one child. And the tree always extends from blue nodes, because when you hit a red node, then it only has one child, which has to be in the matching. Okay, so hopefully this picture sort of recalls some of the pictures you have. We don't need to deal with blossoms, because we're not going to actually, we're doing this on bipartite graphs. But we will use alternating trees. Now remember that the way that alternating trees worked was that you start from a blue vertex and you consider some edge B comma C where C is not in the tree. This is how you extend the tree. If C is M exposed, then you find an alternating path. Otherwise, C is matched, and then you can extend the tree. Okay, now someone tell me, what is the problem by just running this algorithm in this setting? Why can't I just run this algorithm? What do I need to ensure when I run this procedure? Let me show you what I wanted to maintain. So what is it that we need to maintain with respect to the alternating tree? Any suggestions? We need all edges in the alternating tree must be in the equality set. We need to enforce this property so that when an augmentation is performed, the new matching is also in the equality set. Right? This is what we need to ensure at all points. So all edges in the alternating tree must be in the equality set. And so this is exactly what we are going to enforce. So now let's talk about, remember, again, let me show you the alternating tree. And remember, the alternating tree extends from a blue vertex. So any blue vertex, right? It can be an interior blue vertex as well. But from a blue vertex, we find an edge that is incident to that blue vertex, such that, it is incident to an edge so that the other vertex is outside the tree. And we need that edge to be an equality edge. So we extend the tree by an edge BC, where B is in the blue vertices, and this vertex C is not in the vertices of the tree. And BC has to be an equality edge. It must be an equality edge. Right? Because those are the rules of the game. So as long as we can do this, we can continue to do this. Now, when do we get stuck? When do we get stuck? We get stuck when there are no edges of the form BC, where B of t, C is not in the vertices of and BC is an equality edge. That's when you get stuck. Now I'm just going to write a simple claim here. I'm going to leave the proof as an exercise. Is if so my claim is if the tree is stuck, and there is no edge of the form BC, where B is in blue set, C is outside the tree, then there is no perfect matching. And a hint as to how to prove this is basically use the Purge condition. Now we assume that the graph has a perfect matching. We assume that the bipartite graph has a perfect matching. And because it has a perfect matching, we know that when we get stuck, there is some edge BC. There's at least some edge BC, but it is not an equality edge. Right? So the idea is here's the alternating tree. And so here is the blue set. This is the blue set here. Now, if there is no edge leaving the blue set, then there is no perfect matching. And you can prove this using the Purge condition. So we know that because there exists a perfect matching, because we assumed a perfect matching exists, there are these edges, BC edges, but none are equality edges. Right? Because if there was an equality edges, we would just extend the tree. So there are edges that are coming out of here. But these edges, these are not equality edges. So what we know is that YB plus YC is strictly less. Maybe C is bad, because C is a bad notation because C refers to the cost. But Y, let me instead, my apologies. So I'm going to call this, I'm just going to call this little v, so that I don't abuse my notation. So we know that this is strictly smaller than C dv. Okay, so I'm going to draw a picture here to show you what the situation is. I'm just going to draw it a little differently. Remember that the blue set and the red set essentially form a bipartite graph amongst themselves, right? Where the blue set is on one side and the red set is on the other side. Because they're formed, they're basically from some subtree. So I'm going to draw my picture as follows. This is the blue set. This is the red set. And these are all the other vertices. This graph is bipartite. These are all the other vertices. Now there are four kinds of edges. There are four kinds of edges. There are the blue-red edges. There are the blue U edges. So this is the blue edge that is going up to U. There is the red U edge. And there's sort of what I call U edges. These are the four kinds of edges. There are no edges within B. There are no edges within R. This is crucial because G is bipartite. Because G is bipartite, there is no blue or red edge. Okay, this is because the graph is bipartite. Now the question is, how do you update the dual? And one more thing that we know. For all BU edges, which I'll call B little u, YB plus YU is strictly smaller than the cost of BU. Because if it was equal, then we could extend the tree. If it is equal, we could extend the tree. Now, can someone tell me how are you going to update the dual? Now that we have this condition, how would you update the dual variables? Is this picture making sense here? To understand what is going on? So, this is the situation we're at. For all blue U edges, where U is every vertex that's not in B union R, the constraint is slack. The constraint is slack. How are we going to update the dual variables so that we can continue to make progress? What do we want to do when we make progress? What do you want to do when you make progress? You want to increase the number of equality edges. Because then, if we can make one of these edges an equality edge, then we can start making progress. So how would you update, how should we update the dual variables? Any suggestions? Let's look at this. Let's look at any edge. How are you going to make this an equality edge? What do you need to do? Very simple question. How are you going to make this an equality edge? What is the dual change you need to do?
You want to increase y, b, and yu.
Good. So you want to increase these variables to get equality edges, right? But what is the worry that you have? When you start increasing these, you might break other constraints. Right? That's your fear. Can you figure out how you would increase these? Maybe decrease something else. So here's your edge. Okay, so let's just say this is B and this is U. So what could you do? You could increase YB. And you could keep increasing YB until this becomes an equality. What is the problem that's going to happen when you do that?
It will break the complementary slackness for B and the other red.
Okay, good. So let's say you had an edge of this form, right? And this is an equality edge. You're going to break this. So let me call this little r. How would you fix that? So how could you fix that?
Instead of changing b, just change u.
Now the problem with u, okay, so that would be one. But then if you're going to have to do that, you're going to have that problem on this side as well. Let's just say you want to stick to doing things with b and r because that's where your tree is. So you only want to change the dual variables there. So no, you're right, exactly. So you increase yb. So bu, you get an equality edge. But now br has broken. Is there some other change you can do to fix that? I'll write this on. So you have yb plus yr. This is equal to cbr, right? This is going to be an equality edge because it's in the alternating tree. Or it's potentially. You know, you may have these other edges as well which don't, but let's say potentially you have this. So if you increase yb, then what should you do?
Decrease yr.
Decrease yr. By how much? By exactly what you increased. Right? If you increase yb, then decrease yr by the same amount. But now you need to be careful. Now you decreased yr. Maybe this was an equality edge. So how do you fix that?
So essentially, do we solve the NP on like a system of equations on all the edges that are kind of...
It's much simpler. No, it's much simpler. Just follow this argument, right? You know. So it's even simpler, right? So suppose you increase yb. So you have to decrease yr. How much do you increase? What should you do with yb prime?
This entire thing will keep cascading, right?
Okay. How? But why will it keep cascading? Can it cycle back?
Yes, I guess like it will have to get a different kind of edge.
Okay, so suppose it cycled back. Suppose you have this situation here, right? Okay, so here's your situation. Let's just say all of these edges are equality edges, which could potentially happen. What would you do? So all of these edges are equality edges. What should you do?
All the BR edges?
Yeah, let's say all the BR edges are equality edges. Say.
So then you just adjust the UR edge.
UR. You see, in U, you don't even know what's going on. So let's just say for now, let's leave U. Let's just try to adjust the dual variables in the tree. You want to make BU an equality edge because then you can start extending from BU. And as was said earlier, you can increase YB. And if you increase YB, you need to decrease YR. Now, if you decrease YR, what do you need to do to YB prime?
You need to increase YB prime.
Okay, you need to increase YB prime. What do you need to do to YR prime?
Decrease. So essentially there's an alternating.
So can you simply describe what we should do?
So you essentially shift all the YB edges by the difference and like increase the YBs by certain amount and decrease the YRs.
Exactly. So that is the one sentence solution, right? Increase all the YBs and decrease all the YRs. by the same amount. Because if you increase YB by a certain amount and decrease YR by the same amount, then the BR edges remain unaffected by your change. The UU edges are unaffected by your change because you're not changing any values there. The RU edges only decrease, which is good for you because your constraints will still be maintained. Your only worry is with the BU edges, but those are going to increase. So you choose exactly the minimum amount to increase it so that nothing will break. Quite beautiful if you think about it. Does that make sense? So let me now write this out formally. I'll just say among all BU edges, determine the maximum safest increase. So specifically, I'll just say that set epsilon is equal to the min of B in B, U in U of CBU minus YB minus YU. Right, so this is how much an edge you need to increase YB to fix this edge, but you can minimize it over all of these edges here. Minimize it over all these edges and simply add epsilon to all YB, decrease epsilon from all YR. And the claim is that the new Y is dual feasible. Any questions? Any questions about this? The new Y is not dual feasible. Why have we made progress here? I'm going to leave the proof as an exercise. So the proof is going to be an exercise. But I would like, please ask me any questions about this if there are any doubts. I'm going to give you an additional statement, and this is another exercise which is useful to do. Argue that this change increases the dual objective. If you think about it, it'll be clear, because note that you're increasing some of the dual variables, decreasing some of the other dual variables. So it's not clear that your overall dual objective, your dual objective was just to maximize the sum. You need to argue that this is actually going to increase. But that aside, that's not important for our proof. That's just an exercise to get some understanding. The question is, okay, so now that we've done this change, why have we made progress? Why have we made progress?
We increased the size of the equality edge.
Exactly. We increased the size of the equality. So I guess I should say technically we may not have increased because there could be an equality edge from R to U which has gone down. But you're right that we now have an equality edge from where we can extend the tree, which is sort of more important. We get an equality edge which allows us to extend the tree. All equality edges between B and R remain the same. There may be equality edges from R and U which are not equality edges anymore, but we never extend from there anyway. But you're absolutely right that we now gain an equality edge which we can extend by. And this is the Hungarian algorithm. So we make progress. Because a BU edge becomes an equality edge, so the tree can extend. And so this is the process now. So the tree can extend. If it's an augmentation, it goes ahead and augments, and then the matching size increases. If it does not, otherwise the tree just keeps growing, and then at some point the tree gets stuck. You make a dual change, then the tree will make progress, so on and so forth. And again, sort of what is the absolute magic of complementary slackness is when this finally ends with a perfect matching, you have the optimal minimum weight perfect matching without ever having to explicitly worry about the objective. So let me now just write down the Hungarian algorithm in full detail so that you have it in front of you. So this is the Hungarian algorithm for min weight perfect matching. So the first step is we initialize the dual variables to any feasible solution. And I'll leave it as an exercise. It's fairly straightforward, right? You can essentially set all of them to be sufficiently small. You can just make all of them to be smaller because, potentially the weights could be negative. The way that this is set up, we even allow the weights to be negative. So you just set it to be something that is going to satisfy all of these constraints by making everything sufficiently small. So this can be easy. So if all the weights are positive, then you just set it to all 0. Right? Otherwise, you can just sort of set it to be like the smallest possible weight. Like half of the smallest possible weight for every YU. Okay. Initialize M to be any feasible solution and the matching to be the empty set. And then we'll just say while M is not a perfect matching, we initialize the alternating tree T with root V that is M exposed, and then we'll say while there is a B U edge B little u, if U is M exposed, then we augment M, and then we go to step 2. Well, we can go back here, right? Because now that we've increased the M, we can sort of go back and then restart the whole alternating tree. If U is M matched, excuse me, then we extend the tree. So we keep doing this while there is a BU edge. Then we know that if there is no BU edge, just output no perfect matching. Okay. Otherwise, we just set epsilon to be the min over all BU edges of CBU minus YB minus YU, and then we add epsilon to all YB, subtract epsilon from all Y red. Right, so this is the red vertices and these are the blue vertices. Alright, so what is the running time of this algorithm? What is the running time of the algorithm? Give me a crude bound. How many augmentations are there? N augmentations. So there are N loops that we're going to run. Now, each time you want to extend the tree by an edge, you may have to do this dual change. And the dual change in the worst case is going to take O of M time because you have to look up all the edges. So if you just do it a very brute force way, every time you do a dual change, you look at M edges, then you go back and then you do a tree extension, and then again you have to do a dual change. So for every tree extension, you may have to do a dual change. There are at most N tree extensions. So it's N times M for this inner loop, and this whole loop runs at most N times. So you get N squared M. And if you're more careful, then you can improve this bound significantly. But just a sort of crude runtime analysis. So a crude runtime analysis is there are at most N augmentations. There are at most N augmentations. For each augmentation, there are at most N tree extensions. For each tree extension, a dual variable change can be done in O of M time. So the total is O of N square M. If you use, you can use Dijkstra's algorithm, you can use like priority queues, we can get O of Mn log n. So I'll just state the basic theorem here. The Hungarian algorithm computes the min cost, min or min weight, perfect matching in O of Mn squared. Okay, so that covers sort of the main theorem of what we had today. I'm going to state something here that I'll leave as an exercise, but this is a very, very useful exercise. This is related to a question asked in the beginning. Show that the correctness of the Hungarian algorithm implies Birkhoff's theorem. I'll actually prove Birkhoff's theorem, but it turns out that the correctness of the Hungarian algorithm is itself a proof of Birkhoff's theorem, although a rather complicated one, and there is actually a much simpler proof of Birkhoff's theorem that I will state right now. So here's a proof of Birkhoff's theorem. Recall, Birkhoff's theorem said that if the LP that we gave in the beginning, and what is that LP? This is just the LP that we gave was the summation of x v w equals 1 for all v in the neighborhood of all w in the neighborhood of v, with xe being greater than or equal to 0. So if this LP has an optimum, then there exists an integer valued optimal point. Okay, and I'll give a direct and fairly elegant proof of this fact. So consider any optimal solution x that is not integral. That is not integral. We will compute an optimal x prime that has one fewer non-integer coordinate. So what we can do is, I'll show you how to do this, then you can start from any optimal solution that is non-integral and keep reducing the number of non-integer coordinates until you end up at an optimal at an integer solution. Okay, so the way I'm going to do this, I'll just say that let E prime be the subset of non-integer edges or coordinates, right? Because, no, maybe I'll say E hat, not E prime, because that's confusing with this prime. So E hat be the subset of non-integer coordinates in X. And let G hat be the subgraph of these edges. Right? So this is basically, you're going to get some set of edges such that each of these values, the xe, is basically neither 1 nor 0, right? So it's something that is not integral. Now here is the key fact. All degrees in G prime are at least 2. Why is that? Note that the summation of xe, where E contains some V, so here is some V, this is equal to 1. So if one of the xe's is not integer, there has to be another xe that is also not an integer. Right? So if one of these is not an integer, and because the sum of all of these is 1, there has to be something else that is not an integer. So all degrees are at least 2. Okay, now I'm going to make a statement and proving it's a basic graph theory exercise. There exists a cycle in G prime. It's an exercise. So in any graph, you can actually show that in any graph where all degrees are at least 2, there must exist a cycle. And you can just prove this by, essentially by induction, or just starting at a vertex and keep following it until you come back. So there must exist a cycle. G prime is bipartite. So the cycle has even length. So the cycle has even length. Let epsilon be equal to the min. So the cycle, I'll say the cycle C. There exists a cycle C. C has even length. So I'll just say that the min of every edge in C of XE. Let me just look at the minimum. So now I have some sort of cycle. Let me just look at the minimum value on the cycle. And let, just for convenience, and let us order the cycle as E0, E1, E2, going all the way up to E of 2k minus 1. Right, so I could just say this is where E0 was the minimizer. I'll say is a minimizer, right? So I just pick some minimizer, so maybe I get this. So I call this E0, next is E1, then I say this is E2, E3, E4, and then E5. I just number all of these this way. I guess, okay, so technically, sorry, I should look at the min over the set XE and 1 minus XE. I'm sorry. So I look at the min of XE and 1 minus XE, and I look at this minimum over all the edges, and I look at E0, which is a minimizer. Now I'll just say that if x E0 is equal to epsilon. So if the minimizer was basically xe0, then I simply decrease all E of 2i, so all the even ones by epsilon, and increase all E2i plus 1 by epsilon. And if x E0 was actually 1 minus epsilon, so if the minimizer was the other one, then I just do the opposite. So I increase all E2i by epsilon, decrease all E2i plus 1 by epsilon. The resulting point that I get is feasible and has one less integer coordinate. And that ends the proof. You saw the idea was actually quite similar to the Hungarian algorithm, right? Where you have this notion of increasing the dual variable of some and decreasing the dual variable of the other. And it's a similar idea here where you increase. Now the point is, because this is an odd cycle, what you can do is you can alternate the increases and decreases, and you maintain the sum at all the points. Excuse me. So you maintain the sum of the edges, the edge values, because you increase one and you decrease the other. If you had an odd cycle, this wouldn't work out because you would increase this, you would decrease this, but now you're stuck over here. where you're forced to both increase and decrease it, which you cannot do. So when there's an odd cycle, the proof breaks down. But if you have an even cycle, then you can increase this, increase this, decrease this, and you maintain the sum at all vertices. And so this gives a proof of Birkhoff's theorem. Although, as I said, the proof of the Hungarian algorithm also gives a proof of Birkhoff's theorem, but this is a very nice direct proof. It's a sort of classic statement in, I guess, algorithms and in polyhedral combinatorics. So it's I think a very nice proof to see. So with that, I'll end today's lecture and I'll take any questions that you have.